The initial starting point of the conversation is RL, and an interesting question is, what is different about doing RL for coding than for other sort of easier, more verifiable domains? So either for math or for even like sort of even vaguer domains like sort of writing or anything else. What's different about coding models?
Well, one thing is sort of like the action space for coding is much larger. So if we think about math, reasoning works really well for math because the answer is quite short at the end. And so reasoning helps give it a lot of action to arrive to the answer. While coding, sort of like the reasoning is already in the answer, right?
Yeah, also to get to the answer, you have to call like multiple tools. And so instead of just like generate reasoning tokens, generate an answer, get a reward, it kind of looks like you generate some tokens, call some tools, get a response from those tools, and maybe you do this iteratively several times. So the RL, the shape of the RL looks a little bit different because now you have to like go through this multi-step tool calling process and optimize over that.
And for us, RL is particularly interesting because we don't always have a way after receiving the completion from the model of determining whether it actually solved the user's problem or did what the user wanted. You know, if you have a math problem with a golden answer or a coding problem, then you can test whether it gets the right answer. But we want to do RL in situations where the user doesn't always tell us whether it worked or not.
What do you think is going to happen for domains like writing? Do you think we just won't use RL there at all and just hope that the base models like get good enough via pre-training? Do you think like there is a path for RL improving things there?
The post-training that's currently done on the models tends to make them write in like a very stilted and formal way. But I don't think that's like an inherent limitation of the models. I think that's just what they're trained to do.
Yeah, why can't you like train the models to predict the next chapter? Like certainly instead of making it predict the next token, you want to change the learning dynamics so that it starts to predict the whole sequence. Given the current chapter of the book, the model should try to predict the whole next chapter of the book, sort of how the story follows. And then you have some sort of similarity metric on how that next chapter is similar to the ground truth chapter.
It's like taking hard next token prediction problems in writing and then allowing it to kind of do reasoning and then using the reward, some like reward of similarity.
Some like semantic reward, ideally. Yeah.
Because I think one of the limitations of these models is that the next token prediction objective doesn't really fully capture what we actually want, which is generating a full sequence.
Well, there's two things there, right? There's like letting it spend more compute before predicting like the next token effectively, and then there's like it doesn't actually need to predict the exact next token versus predicting like this full sequence that is like similar to the next chapter.
The thing that's hard about writing is that whether the output is good or not is really a matter of taste more than with coding. And with coding, you really just want it to work. Whereas with writing, even experienced people might disagree about whether it's good or bad.
But don't you think there are like facets of that in coding? Like once you get to like it passed the test, like it's going to be maybe pretty hard to get past that, right?
Yeah, that's true. I think code quality is a difficult problem.
Yeah, but pass the test sometimes doesn't work because pass the test doesn't also capture the case of what the model actually did to make it pass the test. So even ignoring sort of like the hacks where it starts doing sort of edge cases to make the test pass, like the model could start doing things that are completely unrelated to the task and still pass the test, and that would give them a good reward, right?
Well, I mean, that's just a function of how good your tests are, right?
With code quality, or like what you want is kind of like elegant code that's like not longer than it needs to be. There's like maybe like you want like the shortest solution or like the smallest description length. Similar with math, like maybe the most beautiful proof is like the shortest one. I mean, it's not exactly the same thing, but I think there's an element of that.
What about with edits? Would you then like bias towards things that deleted code?
If you just want the shortest solution?
Yeah.
I mean, I think it's great to delete code. Yeah. If you can do a minus 100 line PR that like keeps all the functionality, like I'm very happy.
Yeah, no, that's fair.
What are good rewards in general? So I think the topic came to like these rewards. I think we're experimenting with many different kinds of rewards for training the RL models. What are some of your favorite ideas?
Like what are the pros of tests then? Like
it's like very close to ground truth. So like he said, there's some issues with tests where like maybe if there's not enough coverage, you can kind of skirt around them without solving the real thing. But if there's good tests, then it's something close to a ground truth signal of like, does this code work or not? And you can like really do RL against that for a long time. and learn some potentially interesting behaviors from the model. But, you know, not everything can be captured by tests. So like we might need to sort of relax sort of the conditions and maybe think about other ways to get rewards. So this could, like one idea is potentially like using, you know, a ground truth diff of like a change for a feature. And, you know, maybe there's multiple ways to make that same change. So it's not a perfect, you know, signal, but like you could potentially use this as information for helping, you know, make a verification signal.
What about like the sparsity of reward and tests? Like maybe one downside is you have to sample a lot of rollouts and you only get like one of them passing. You only get this kind of 1 or 0 of like, did it pass all the tests or not?
Yeah, I mean, it makes the training like computationally expensive, I guess. But like, there is this like interesting thing, like if you have enough compute to do a bunch of rollouts, you can kind of get sparser signal by doing rollouts from each token in sort of a branching way,
yeah.
But it becomes expensive. So basically like the sparsity just converts to like a expensive compute problem.
Because the models actually don't see the reward, they see the advantages, which is sort of like a reward relative to the reward other rollouts from the same prompt.
Well, the interesting thing is, like one thing that would be quite useful is, normally if you have tests on a full PR, like that's going to be super difficult and super sparse unless you spend a ton of compute, right? Because very few times in like a full PR is maybe like where the models are today, are they going to be able to pass all the tests? But maybe like what you want is you want to be able to break it down into smaller parts of like the full PR and then get tests in that. And that probably would just be like, would that, if you had the ability to do that, would that be like a strict improvement?
Yeah, I think that probably would be. So I guess like, yeah, there's this problem of like, if the task is like so hard, the model will only get it right like 1 in 1,000 times if you just sample, then the sparse reward becomes like a real issue. If it's, you know, 1 in 100 or like slightly higher than that, then like you can probably work with that. But yeah, so then once you have it at that sort of like 1 in 1,000, maybe you need to think about like breaking things down more. Or
do you think we're in that regime, full commits, where it's like it might be a bit too sparse?
Yeah, I think in some cases you may need to reduce the amount of sparsity by breaking it up into component parts and wanting it to get each part right. I mean, on some level, I think what you want is like a change that's equivalent in functionality to the ground truth or the good change, and that's short. The problem is that not only is that a difficult objective, but even like evaluating whether a candidate solution like satisfies it is equivalent to the halting problem. So it's like, it's very hard. You can't actually do that.
Yeah.
But if you can do something that gets at it, maybe that's a good direction.
What are the most interesting tools? So like generally, you know, we've seen this trend of like different sort of labs choosing different sets of tools to RL the model for. So O3 sort of very, very optimized for terminals. And, you know, it tends to like, it's this kind of very weird model where it only tends to sort of grep and set and doesn't use, you know, it doesn't want to use any tool other than terminal. And then sort of Claude models that tend to maybe designed around sort of searching and editing. There's some interesting ideas around tools that, you know, one would use that aren't just the sort of traditional tools.
I mean, I think you can do a lot better than the kind of core set of tools. I think the reason why the terminal makes sense is it's so easy, right? Like you don't need to build some super fancy harness in order to run your agent. You literally just give it access to a shell and that can just do everything in there. Simplicity is probably the biggest reason, right? So the one example is like linter errors. Linter errors give you a ton of signal, but they're just hard to get because you need to run a language server in order to get that. And then actually getting a language server running for arbitrary code is actually kind of hard. But, you know, it's an interesting thing that we have as Signal in Cursor because, you know, Cursor comes with extensions that have language servers pre-installed and users will go and set that up. So you get things like linters. We also have something like semantic search. And I don't know, like, I actually don't think semantic search can get you things like over just static code files. It will get you things that like grep with sufficiently many hops could get you, but it'll get you there faster. And so that means it's cheaper, using less of the context window, and faster.
Right, so maybe this gets to the point of you also want to improve the quality of the tools. I don't know, how do you guys think about picking high quality tools versus trading
like
off the
minimal.
Simplicity of, like, you can sort of pick the most minimal description, which is, I guess, just the terminal, and then you could ask questions like, maybe you want higher and higher quality tools for the model.
Well, one thing is sort of you can also use tools to model the behavior of the model itself. Like, for example, we know a lot of the reasoning models like to reason a lot and overthink, even in situations they don't really need to start reasoning for. So one way you can sort of mitigate that is if you add a thinking tool where the model realizes the task requires some reasoning, and so then it starts calling the tool to enable this reasoning.
Yeah, I've always found like the way the reasoning models interact with agentic tool calling. Maybe O3 is a bit different. I haven't played as much with that, but it was always kind of weird where it would think after you submitted the user message before it like had even seen anything, and then go and call these tools.
And so what you mean is you think the model should think after each of the tools, right?
Not after each of them. I mean, I think what was the reason that people train these reasoning models, right? And how did they normally train it? It was when, I think like the first version of O1 was probably just trained on competition, like competitive programming, and then math problems. And like the idea there is you want to, at the end, like come up with some nice answer. Either you can show that to the user, or you can like show this to like whatever's and grabbing that and like verifying it. And then before that, you want to like spend a bunch of tokens thinking. I wonder with agent trajectories if like what is the thing that you're actually showing to the user like want to be verified in the end, right? It is either you're like there's some text maybe that like the user gets to see, but a lot of the time like when you're not asking it a question, you're just asking it to make the change. It's like literally just the edit tools, right? When it's like editing a file. So I wonder if you even need this concept of there is separate reasoning when you're just asking a model to like edit code. And just like it just does whatever in those tool calls when you train it. You let it do whatever instead of restricting like some like nice reasoning section.
Another like really interesting tool that we're thinking about is looking at PRs and what the people in the code base have been doing. I mean, like one like mental model you can have for these models is that they're capable engineers who are like perpetually on like their third day in the job. Right? And they get like 2 days of like context to like try and like get up to speed in the code base as quickly as possible. And then, day 3, they're asked to do something. And, if you were in that situation, I think, one reasonable approach would be you spend those 2 days trying to understand what your colleagues have been doing and like why they're making the changes that they're doing and what code are they touching. And currently, the models aren't really oriented around looking at PRs and looking at what the people have been doing. They're more designed to consume the code in large chunks and search for relevant code, which is a great match for how these models were pre-trained. And obviously, it's still an important part of the solution, but something that also looks at the PRs is interesting to us.
How do you think code and long context interact? So at least in some weird way, like, you can sort of say long context is very important because if you look at restrict everything to 8K tokens, like Sonnet and O1 and GPT-4, like the original thing, are kind of equivalent. And so you need something more than a critical context length of like, maybe you need 50, 60K tokens minimum. Do you think you just keep letting the context length go and that improves the RL? Like, how do you think the two interact with each other?
I mean, the trend has been for the context to get longer and longer, and attention is pretty great at using a long context, but the price also gets higher and higher. And so on the technical side, I think a really interesting direction in long context is, how can we keep the costs low? How can we reuse cached context across many prompts? And that gets, particularly relevant with the most recent models that are like more capable than before, but also, the total bill can get quite high if you're not intelligent about how you cache and use the context. And, when you start looking at professional code bases, there's like a really large amount of relevant context to whatever you might want to be doing. And it's something that I think is maybe special to code in some sense, in that, if you are ChatGPT, right? If you are the Claude app, there's not that much context that the user is bringing in most cases. They have a question, it's often 100 tokens. And so your main concern is how to like compress the totality of human knowledge into weights and then use that to give a good answer to the question. You're less concerned about how do I take 1 million tokens and get useful information from that can be efficiently used by a model, because it's not what most of your users care about.
How long of context window do you think we need? 1 million, 10 million, 100 million?
I think longer is better, but there are also diminishing returns. The approach of retrieving relevant tokens to the query on the fly is not the only approach we need, but it is also pretty good. And so something that uses a mixture of mechanisms of having some kind of mechanism that, for example, can consume 100 million tokens, but maybe, gets less information from each of those tokens, right? And uses that to get a general understanding of the code base. But then when you know exactly what you want to do, it can remember which parts are relevant and refresh its memory on those parts, is probably what will make the most sense long term.
What do you guys think about all the new architectures coming out where sort of, there have been some trends where it sort of reduce the, there's normal sliding window attention and, more and more you have found these, Llama 4 has an even more sort of complicated attention mechanism. And
yeah, I mean, NSA is pretty elegant, right?
What's your take on NSA?
Actually, elegant may not be the correct way to
so
describe it.
So NSA here is DeepSeek's attention mechanism that they publish.
Yeah, it's DeepSeek's, and fingers crossed that they're going to release this in their next model. But it's their attention mechanism that scales quite well. They found it performs better than attention, and the core way that it works is kind of splits up attention into these three pieces. One does sliding window attention, so kind of pays attention to what happened in the short term, the last, I don't know, maybe in 4,000 tokens. And then the other two parts are kind of interesting because it basically does this blockwise attention where it will, every some number of tokens, kind of store that as a key and value. And then the query will attend to those. And then from that, you get the top K blocks that you want to fully attend to. And then you take those blocks and then you actually do full attention on them. I think it's pretty cool because, yeah, it kind of should do a pretty good job of retrieval across this long context window.
What do you guys think about? I guess NSA versus we internally care about more on a file level attention or something like that.
Yeah, I mean, what do you think about NSA?
I think it's taking the ideas that make MOE work and applying it to attention, which is, we have this playbook for introducing sparsity into models trained by gradient descent, which is you get some values, you do a top K on them, you do a softmax on the resulting values, and this is how MOEs are trained. And the idea is that even though you don't get gradients for everything, the fact that it encourages the gate weights to be larger for the more relevant, in the case of MOE experts to a particular example, means that the sparsity mechanism can still learn to route it to the most appropriate expert, and in the case of NSA, to the more appropriate chunk of the context. So it's really just I think developing that and applying it to a different area.
Do you have any other favorite attention mechanisms?
The hard part about evaluating long context mechanisms is, to really get a good sense of the baselines, because, everything kind of works to some extent. You can do sparse attention, you can have some heads that attend locally and some that attend globally, and these all make performance a little bit worse and make it faster, and so you have to be really rigorous about evaluating these things. I don't know if I have any specific favorites.
Things like add a memory tool, so this interaction with somewhat adding state to RL terms, where you can store a piece of thing and hopefully retrieve it later, but the problem being sort of how exactly do you encourage the model to actually store good, useful memories that will be useful for later? What do you guys think about how RL will develop to let you do much more complicated stateful tools?
Well, it's interesting. It feels interesting how much things have moved in the direction of not everything being in the model versus the model being able to take actions that let it do everything, right? Instead of having a really good long context model that can do retrieval, it's okay, the model now is really good at just using this tool of retrieval, and that's either search via semantic search or the way that it was trained, grab.
The memory tool is super interesting because there are actually really two tools. The first tool is I want to store a memory of this particular interaction, and the other one is I retrieve it. And sort of retrieving a memory is quite straightforward to teach to a model. You can just give a reward if retrieving that memory actually helped in the conversation. But storing that memory is way more complicated because the reward is not dependent on the current trajectory, is dependent on different trajectories. And that also increases the computation during training, because it means that basically to get good signal from storing this memory, I have to do many rollouts in a bunch of random other trajectories that are completely unrelated.
Yeah, exactly. Like once you do the writing, you're storing something to state that you'll use in a future trajectory. So when you do the training, you're going to have to both do the rollout to store it and then subsequent rollouts that retrieve it and apply the reward and back it up to the writing step.
Yeah, it's probably much easier to do like a non-model training way of generating and retrieving memories. We were talking about this the other day, and instead using like the system that Federico described as like evaluation across like trying all these different ways of generating and using and grabbing memories.
Well, how should we evaluate memories?
I mean, did you have the idea there, or was it Luke?
I think it was Luke, actually. Because of the credit assignment problems Federico mentioned, it is really hard to like actually backpropagate into the memory storage mechanism. So instead of that, you get a benchmark of, let's say, like 500 examples of like stuff agent is supposed to do and a way to check whether it did it. And then you just experiment with different like rules and heuristics and prompts for like when to store a memory and when to forget it. And you just measure how well each of those does. And that's not enough examples to backpropagate into something because it'll just very quickly learn to like reward hack on them. But if you have like a system of heuristics, it can maybe help you find the best one.
Yeah, I wonder if things will look like memories make sense to do in the short term. I wonder if that's something that will persist for the next year, or will it be some kind of more long context mechanism like Jacob described, where maybe it sees all your previous chats and can kind of strengthen.
What do you guys think of previous chats mattering versus all the previous PRs the user has?
There's two kind of different things, right? Previous chats feels like a lot of the time, well, there's some similarities, some differences, right? Like one thing that you get from previous chats, which you don't get from previous PRs, is like actually doing things and seeing like how your environment reacts, right? And then you can kind of update from there in a way that you don't quite get with PRs. PRs is just kind of demonstrations. Yeah, I think they're both useful for different things. Like, I mean, also you just like are using things that like you never really see in PRs. Like you're seeing like the terminal, you're seeing how like the linter reacts and how like your auto formatter might react, stuff like that.
It does seem like you can get some like similar personalization from previous PRs. Like if you have a bunch of PRs in a code base, you can kind of get a sense of like what kind of change, like this sort of, if there are certain stylistic jumps you have to make in a code base to make certain edits, you could learn to do those regularly.
Yeah.
Like first I change this file, then I change that file.
Yeah.
I'm very hopeful about the whole long context story because, I mean, I sort of hate to be the computer guy, but the new generation of GPUs really make long context very easily. Like the GB200 NVL72 architecture allows to do very long context quite easily in two ways. One, because you have these 72 GPUs that are all interconnected in the NVLink mesh, you can do tensor parallelism that is above the sort of 8 GPU mesh. And what that allows you to do is you can reduce the number of attention heads per device where you store the KVs. In addition to that, the sort of like Grace CPU allows you to have this unified memory on which you can store the KVs, and therefore that allows you to store a much larger number of KVs per device.
Yeah, I mean, the really cool thing that you could do is, we've heard of people trying this, is you actually don't need to store your KVs on the GPU memory, right? Mm-hmm. And you may be able to incur like next to no slowdown because you can basically interleave computation with then loading the next time it goes through attention, loading those into GPU.
Yeah, when you get to like layer 0, you start offloading from the CPU the KV that you need at layer 1. And so it's basically free. You never need the KVs, the full KVs to be on your GPU memory, except when you actually get to the layer.
Yeah, but I mean, this will only scale to like what, like 1 million contexts? Like you're still gonna have to pay this like quadratic cost, and that's always gonna like you can get over like the cost of just like literal memory.
Yeah, but it's still sort of like, if you make your parallelism right, it should still be like 72 times cheaper, right? Because if you shard the attention heads correctly.
It'll be 72 times cheaper, but 72 times cheaper for this like massive n squared blow up. And so like maybe you need like the 1 million context with all these, like people are adding all these constant factor things to make it better, right? Like sliding window every so often, maybe sharing. I mean, NSA is another great one. It's a big constant factor, but it is a constant factor.
do we think about document level attention?
We love it.
Yeah, we call it squid attention because we envision it as a squid where each document is like a different tentacle.
Oh, is that why?
Why do you think?
I don't know. I had no idea.
Who came up with the name squid attention?
Lucas.
It's not a very Lucas name. The idea with squid attention is you basically want to independently attend to each document. Like each document will independently attend to itself, and then at the very end, you then attend to everything. And the reason this is good is you can now kind of swap out documents. If you like care about like 10, 20, 30 documents, I can then just go and cache the keys and values of each of these documents independently and never have to repay the prefill cost. And I can just sub them in inference time. And this is like really useful for like all kinds of features in the product, right? Like for tab, it's really useful for when you're retrieving things and want to do it quickly. For agent, again, when you're using semantic search, when you're reading files, this would be like immensely useful.
So I think we brought this up in the beginning, but like optimizing a lot for sort of test usage is like one way that RL has initially been done. But do you guys have crazy ideas for how you should optimize more for real world usage where humans are using the thing that is not just optimizing for test coverage?
What do you mean by that?
For the most part, right, RL is being done to finish a bunch of test cases. And for the most part, what we care about is not actually the model doing test cases. We want it to be very good at add console logs across the file. We want it to be good at all sorts of things that are more sort of human-centric than they are for like sort of finish a particular small task and pass a bunch of tests. This is maybe an indictment of SweetBench, which I know Federico does not like.
Yeah, I mean, so like if we want to get sort of these more, they're sort of like more human rewards that kind of get to like taste, like you want code quality or maybe like printing out the right thing. It seems like to get that, what you will need to do is like get some real signal from real humans in the environment. Did the user like the changes the agent made, or maybe some proxy for that based on like whether they accepted the edits or?
Yeah, I mean, I think there's like probably a lot to do with like just looking at what the ground truth change the user made was, and then from that, getting a good sense of like if when you re-roll out the agent it did something similar. Because like the user will go in and like if it's wrong, they'll just like do something different. I think there are a lot of cool things too you can do when you have something that runs in the background, right? And you can, for example, have it take 3, 4 attempts at the problem, try a bunch of different models, try a bunch of different make the temperature high, and then choose like I'll just go through all the options that Cursor provides, and I'll choose the one that works, right? That's a really good signal for training a reward model.
Sort of amazing how the passat k, which is like the proportion of times the model got it correct out of k tries, is so much higher than the passat 1, which is how many times it got it on the first try.
There are tricks you can do even without like a great oracle or even a reward model of being able to then go, maybe not get all the way to the passat k, but close the gap a little.
Yeah. So like if you sample multiple, you could take a majority vote, or you could like have a reward model that selects the best one, and you can kind of close the gap a little bit.
If we did have the reward signal, like a lot of data on the reward signal of like there are that many rollouts, users always choose 1 of 2, 1 of 3. Yeah, how would we do RL differently? Would we train a reward model just against that signal and just focus on that?
Yeah.
Like the other nice thing is if your reward model sees the ground truth, right? It kind of like knows more than the original model, or like it knows more than the policy,
and,
right?
You can't saturate it, right? Because the problem about RL against reward models in general is that after about 200 steps, you're sort of done. The reward keeps going up, but the model actually doesn't improve.
Why can't you saturate the one that sees the ground truth?
Well, at some point, you're definitely going to saturate it. But since it's grounded in some reality, my sort of hypothesis is that it's going to saturate much later.
Yeah, the problem with reward models is like, the reward will go up forever, but like the real reward you care about will go up and then down. Yeah. But if we're closer to the thing we care about, maybe people are making a real decision in the loop, then...
Sorry, I was just going to say, like, do you think then that it'll be worse? Like, so would it be worse to then trade a reward model against this like really clean signal versus having the reward model that can like see the ground truth?
Well, if you have the opportunity to retrain the reward model, then it's sort of there is no issue, right?
So you think then if we can retrain that like choosing between pairs reward model, that would be a better path than like the ground truth initial.
And I mean, it turns out that we have basically infinite human feedback. So we are in a good spot there.
Yeah, we're in this interesting position where for many of these models, we are the interface between the model and the real world, at least to the extent that the model is used for coding. And so in some sense, this should be our job, is to make the model like match what people want in the real world.
Yeah, I think there's like a trade-off between like, if you can take infinite samples against the real world, you can just optimize that and it'll be great. But if you have sort of a constraint, like those samples cost a lot, you need to think more, and maybe we need to bring in a reward which has the ground truth or something like that, so we can optimize more offline without real users. But
do we think it's within the realm of possibility to like roll it out, like to actually get real reward signal from the agent model by rolling it out to users very frequently? What's the reason not to do that? Jacob might have some opinions.
I
think we should do it.
You think we should do that?
Well, I think to the extent, the way I put it is the shorter you can make the loop between a new model being trained and it starting to interact with the real world, the better your results will be.
I'm more bullish on using a reward model and just retraining that more frequently.
Yeah. Like if you do it every couple days, maybe there's enough diversity there.
Did you all see the thing from OpenAI's retrospective blog post on the sycophancy, where they blame the fact that they trained on thumbs up, thumbs down for the model starting to become sycophantic?
Thumbs up, thumbs down, yeah, definitely is a terrible signal, I can imagine. Because it's biasing the distribution, right, towards this like cohort of users that would press thumbs up, thumbs down.
Yeah, I would never press it.
It's an eval. I think it's like an eval.
What do you think about people that there are probably some percentage of users that just puts thumbs down or thumbs up on like opposite feedback? Just to mess up with people.
Well, the sycophancy would imply that there is like a kind of thing that is pointing in the direction of, right? It didn't go into like nothing.
Yeah, I mean the feedback has to be aligned with the user, right? Like you need to get feedback in places where the user is willing to give you feedback, because they are incentivized.
Otherwise, it's a proxy. Yeah. Like you want it as close to like what's really helping the user as possible.
Yeah, you want to really truly optimize for like the smile of the user.
We want.
Wait, I didn't even realize that was I didn't see that blog
post. They put it in the post. Yeah.
It's because of that.
Well, it's because of that many things, but they said that was maybe like one of the main factors. I think they said something like that.
One real use we could have is like we have the model selector. Like if they switch off of our model, that could be like a real world signal of like, are they happy with what the results we're providing? Yeah.
Jacob. I like Jacob's signal the best, right? You know what I'm talking about?
Oh, just whether the code sticks around.
No. This is the long-term signal that you want.
Oh, just if they churn from cursor, you don't reinforce it. Yeah. We want people to stick around and be happy.
Well, I wonder if we can use churning actually as a way of deriving a reward, right? Like we can, like churning is the ground truth thing. Like we want to like optimize for, minimize churn, and then like can we use that to like predict a reward from like shorter term signal?
It's bias variance trade-offs all the way down.
One sort of similar question on this, and it was like, I feel like all of this debate has been centered around this sort of like outcome-based thing, but the outcome-based thing really was reinforced around the time of R1. And for a long time, people were really into these process reward models, but
what happened with process reward models?
And then PRMs, they're all gone. What happened, Charlie?
So the problem with like PRMs as they were sort of have been practiced, where you just pass the trajectory to a model and you get a score at each step, is like models aren't that accurate at just like providing a score, especially intermediate steps. It has to like make a prediction about like, for certain tasks, like will this lead to the right answer? And so what happens is like once you apply optimization pressure against this reward model, this verifier model, it like you can only optimize for a little bit. It's similar to the problem we're talking about. But if you have these ground truth signals, you can just optimize forever, like math answers. And as a result, you take like 10, I think DeepSeek R1 took 10,000 RL steps. Most RLHF pipelines only do like 100. Once you can do 10,000 RL steps, the model can start to learn like truly interesting behaviors that are very different from where it started. And so, yeah, it really is just about like how much optimization can you apply against it. And with a PRM, You can apply some, but it's limited. It's not nearly as much as you can with these true outcome rewards.
And it becomes worse as many steps you take, right?
Yeah,
So like in a multi-step scenario, you take 50 tool calls, it becomes sort of harder.
Yeah.
It's also why people are being more using the variants of PPO like GRPO or RLU, because the value model is sort of bottlenecked on your trajectory.
Yeah, so like for hard tasks like math and code, I think, just expecting the model to produce a good value, it's just like a hard cognitive task. They struggle with like providing really accurate values. And so, yeah, people do GRPO, you just like do the brute force multiple rollouts to get a value. And that's like much closer to the ground truth. Yeah.
I may have missed the first part, but like that makes sense for like process reward models versus like true outcome reward. But what about like process reward models versus like outcome reward models?
So like a process reward, actually, like if you compare head to head, like a reward model that's just producing a reward at the end versus one that has like these intermediate steps and maybe you're doing search against it, like there's an advantage there. But it has the same problem of like but in both cases you can only optimize so far.
Does that mean we're going to train process rewards? Like, wouldn't that mean like, okay, we kind of decided like one of the reward signals we'll chase after is reward models that we like retrain after so often. Like, should we train process rewards?
Yeah, it could make sense. I think like
or process reward models.
Yeah, like if we want to squeeze out every bit of like information we can get from like the each round of user data, like it could probably give us some win there.
So I guess that moves us to the infrastructure question. Many of you have been involved in building the RL infrastructure. Any interesting thoughts there?
Yeah.
What is good RL infrastructure?
One thing that is interesting about RL infrastructure is just it's naturally more complex than training infrastructure because it builds up on it. Like everything that you use to do the forward and backward for just SFT or pre-training, you need that to be performant for RL. The other interesting thing is now you also have the inference component. And the inference component also has to be optimized in this regime where you don't really care about latency like you do for your users. You care about throughput. You care about getting as many rollouts as possible at scale. And for algorithms such as GRPO, it's also even more interesting because you have one prompt and you are generating many completions for this one prompt. And then eventually you're going to backward on all of these completions for that one prompt. And for math, people in open source don't really care about this fact because in math, most people in open source optimize for like this math tasks. You have like these very tiny prompts, and so you can just forward and backward through all the sequences without caring that you're recomputing all the time the prompt. But for our case, for when you have agents, we have like these massive prompts, and so we cannot afford to backward through all of these rollouts that share the same prompt. And so you start to make optimizations where you overlap more with the inference server, where you start maybe like you already have the prompt from the data loader and you start getting the KVs from that prompt while the inference server is already working on the rollouts. The rollouts come back. You already have the KVs, so you only have to forward through the rollouts that have came back. And then when you get to the backward, you sort of are already prepared the KVs for your prompt, and so you can reuse those and only backward like once on those KVs. So there are lots of like these interesting optimizations you can make that haven't really been done before.
You also need to like be able to quickly like sync the parameters between like the train machine, like the training nodes and the inference nodes. Which is another big challenge.
Yeah,
and that's super interesting as well. Because there are like different situations people do for like generating these rollouts. A lot of people do them asynchronously, where while basically you are while you are backwarding through the current rollout, the model is already producing the rollouts for the next batch with the stale weights. So like the model that's generating the rollouts is sort of like one step behind. But this way it makes training much faster because on the next iteration you don't have to wait for the rollouts to be done before you start backwarding and forwarding through it. And when you need to sync the weights, you kind of have to stop the world and do this like this sync, which happens typically through like RDMA, or you just read directly through the memory with InfiniBand or Rocky or something.
On the throughput side, what do you think you do differently now?
Some of the stuff DeepSeek did for their serving setup for DeepSeek v3 was throughput oriented in that the tokens per second was not that high, but the overall throughput of like number of tokens sampled per GPU dedicated to decode was very good. So that's something that I think they use it to serve DeepSeek, which is quite reasonable, but it is maybe even more appropriate if you're doing RL to make those trade-offs.
And on the NVL72.
And also PD disaggregation, right? That's like super important for RL because you only need to do prefill on one prompt, and then sort of like
I see.
All your decode workers start to spin up and help you out.
Yeah. I mean, one other interesting way to do RL where you don't have to think, in some ways it simplifies things, in some ways it makes it more complex, is if you reuse the inference that you do for your users as like the inference that you're actually doing for RL. I mean, Jacob is kind of working on this for Tab.
Yeah, as long as you don't need multiple completions for the prompt, if you only care about what you actually did, and then you just want to like reinforce or not reinforce what you did, you don't actually need a separate like inference component for the RL training process. You can just look at what actually happened with the real user. It's a different set of trade-offs compared to something where you resample and then compare them using a reward model, because it relies a lot more on being able to roll out a new policy very quickly. But it ensures, a great match between the policy that you're optimizing and the policy that actually generated the trajectory. We're looking at this for Tab because we just get so much data per unit of time, because we get feedback whenever someone is shown a Tab suggestion using Cursor. And so that's just a very large volume of feedback, and so we just have a lot of data. And so we think maybe this can make sense in that case.
Yeah, I think there's like a variance thing with RL where basically like by default that you have like these very high variance gradient estimates, and so if you have a giant batch of like these reinforced like single rollout trajectories, that's fine. If you don't have a giant batch, you need other ways to reduce the variance, and this is where like GRPO comes in, or you can train value functions, and once you add sort of that baselining into the RL, that's like meant to reduce the variance of the gradient. So if you have like an enormous batch, in theory, large enough batches should work.
Large batches and short trajectories. Tab,
exactly.
The trajectory looks, like a couple hundred tokens up and something like that, compared to Agent, which will happily roll out 10,000 tokens.
Yeah, the variance of the trajectories is huge,
Yeah. How can we increase the action space of Tab so that RL is sort of more amenable?
Like other things that other types of suggestions Tab can make?
Yeah. So like Tab, if it only produces one line, you'll have to do many rollouts before you get a different suggestion for that prompt, right? So one trick sort of to make it more amenable to RL is you start adding more actions to it, right? Like jumping, for example.
Yes, jumps are a great source of extra actions for Tab, because if there were no jumps, it would often have to stop the trajectory. But if it can jump, then it can keep going, and it can get feedback on whether you accepted that jump and then did something at the jumped location.
Yeah. I mean, what do you think about, we talked, you just talked about this, but like GRPO versus any of the other RL algorithms?
Yeah, so I guess like kind of the high level difference between GRPO and PPO is like PPO has a value function. Yeah. So this has some advantages for people who don't have a lot of GPU memory, because now you don't have to store a extra value function weights, but at the same time you're doing more flops because you have to do multiple rollouts for GRPO. So there's sort of this flops memory
trade-off. It's not the GPU power.
Yeah. So like you can train the model, it won't but it will take a long time to train.
Exactly.
But yeah, ultimately, like I think especially in like these math code settings, the value function isn't very accurate anyways. Like this goes back to the PRM thing. You're doing a forward pass through the model, it's providing some value. It's not really that accurate, so it's not helping you that much. Instead, if you just like do multiple rollouts and sort of take the average and use that as a value for the question, then like that's a better value than you're gonna get. It's sparser, but it does like it helps out. Yeah.
Before GRPO, there was a very similar algorithm called RLU. Why people didn't care about that
That's a
as
good
much
question.
as GRPO?
Well, also GRPO has been around for a long time. It came out with the DeepSeek math paper, which was like over a year ago, I think. It was 24, like beginning of 24 or something.
I think RLU was like 2019 as well.
Oh, okay. That's even older. Yeah.
Yeah.
And people, I think it might just be like RL became more popular in general with DeepSeek R1, and with DeepSeek R1 came GRPO, so people were paying attention. But like even GRPO existed before R1, like over a year before R1 came out, I think.
And they were using reward models back then.
Or they were doing RL on like the ground truth. I think they also tried RL against a PRM in that paper. Yeah, it is interesting why that didn't result in the same result that we saw in R1 when they were doing it back in the DeepSeek math era. Yeah.
Why do you think?
So there have been some interesting work on this, like trying to understand this, and it seems like there is something with like the base model capability, like either something in the pre-training data or the models just got good enough where they, on their own, the base model will do some amount of backtracking, maybe not very often, 1 in 100 samples or something, but that's enough for like once you do RL a bunch, it'll pick up on those behaviors and amplify them. And so it might just be like the base models got good enough to where they could learn these interesting behaviors.
But does anyone even reproduce R0?
R1 0? Yeah, I don't think there's like a very, there's sort of small scale reproduction, especially on toy tasks.
I guess
but
it's
a large
expensive and really
scale
hard,
on math.
right?
The problem is sort of that, so people have sort of reproduced a similar result on like the Quan32B models. The problem is to make infrastructure that allows you to train the big DeepSeek model. That's like a big lift, right?
It's a lot of compute.
And also the data, right? Like DeepSeek got a ton of RL data, and we don't really have that in open source. We have like this 100, 200K example data set.
I mean, you see all these results where like it's like 1,000 steps and it's on like CPU offloading in order to get some results.
Or like 1,000 steps. More like 50 steps. 40 steps.
Yeah.
Okay, so last question. What do you think is the future of coding agents?
I think
They're going to use way more tokens.
Yeah, we talked a lot about input context, but I think output context is going to be a big thing. Like, especially if you look at like O3, it's a very different agent than some other models where it will just grep forever till it builds up the right context and then knows how to solve the problem. I expect we'll see models which can like do very long sequences of tool calls before they.
It feels like it's wasting all that because it like does probably similar-ish things, and then like that gets like thrown away right the next time it comes in.
Yeah.
It feels like for most things, like you probably don't need to do that much thinking, and you can reuse the thinking that had happened previously, right?
Yeah. I think you should be able to like amortize some of this. Like basically like have an agent that like looks at the trajectories or looks at previous things that have been done in the code base and like makes useful inferences about it and like, stores that somewhere.
Yeah, like it would suck if the world looked like to use the best agent like that, or to use an agent that was like sufficiently good, you had to use like an O3 speed and costing.
Yeah, it should be able to like reuse some of that like knowledge buildup, do it in the background, and then when you ask the question, it should be able to do it very quickly.
I think long context or some kind of code-based specialization will be really important. I think something where it's able to it's kind of like able to reuse work that it's done in the past, is able to kind of get a rough sense of how this code base works. It doesn't have to like redo every single time the work to kind of understand how to make this. Like I think it'll just make it more efficient in like output tokens it needs to actually produce an answer.
What do you think?
The other thing about the fact that you can scale up output tokens, it makes training even more sample efficient, right? Like typically in SFT, we have like these big prompts, and the model really only gets signal from the output tokens.
Well, it makes it kind of inefficient too, right? Because if it's a super long output, like you need to do credit assignment of like what are the tokens that matter, and then like with GRPO, if we're doing it our way, you're just sampling at like every few tokens, like in this massive sequence. I guess it gets data efficient.
Yep.
Is it data efficient? It's data efficient, but not compute efficient.
Yeah.
I mean, I do think we are kind of in this, or approaching this regime in general for like LM training where like sort of the highest quality data is becoming more scarce relative to how much compute is available.
Yeah.
Like the best data is much more scarce than that. So like how do you even use all this compute? And so, potentially methods that look very compute expensive are like
Yeah,
fine.
yeah.
Okay. Call it a day.
Yeah.